Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to take a look on the calculation of loads on silos based on the ACI 313-2016 design requirements. Of course, I cannot show the entire document in its entirety. However, I will only show some of the equations for educational purposes. With that being said, we are going to prepare an Excel file, which I have done already in advance. And I'm going to explain to you the Excel file that I have prepared for you in this video. It's going to be a little bit of an abstract video because, trust me, it took me more time than I want to admit to prepare the Excel sheet. So, okay, our entire goal is to calculate the loads on the walls and on the hopper. And for that, we have two load conditions. The first load condition is the initial filling load condition, which happens when you fill the silo with material. The second load condition is going to be the emptying load condition when materials are flowing in the silo. And for that, we have the Excel sheet that I will upload, and you will find the Excel sheet in the description. Of course, two disclaimers. The first disclaimer is that this video is going to be a little bit more on the theoretical side. There might be some robot action in the end, but I will not be able to apply loads on robot yet today. However, I might apply some robot ideas about connecting the columns to the walls. So the second disclaimer is that some loads are ignored here or left to the viewer to include, so please notice that you should get a copy of ACI 313 and check out any load I have left not untouched or uncalculated. I will try to give the clearest of indications whenever I am ignoring something or I am simplifying something. The second disclaimer is that this Excel sheet is for educational purposes only, so please, if you want to use it on your own project, then use it under your own responsibility. So at least you have to check that out. Okay, so first things first, you need characteristics for the stored materials, and notice all the cells that need your input are in orangey colored. So the density, I've taken it from the material inputs table, which is the ACI 313-16 in the commentary 6.3.1.3. And I mentioned before that if you have the materials characteristics from laboratory reports, then those will take precedence. Please notice also that this is the third part of a potentially four-parter where I have talked about the general principles of silos in video number 1, which is going to be linked above, and about the initial modeling in video number 2, which is also going to be linked above. So please check those two things before you continue with this video. All right, so there is minimum and maximum angle of frictions. Some of the materials in that table provide you with two friction angles. Also, there is effective internal friction. Please notice that I have covered that before. And there is coefficient of friction against concrete, against steel. I'm obviously selecting some cement here. So I took those values from the table. And I used the average of internal friction and the average of effective friction in my calculations. This is, however, an approximation because the code here says that's like in the commentary 6.3.2.1 is that the design professional should consider the appropriate degree of variability in all of those things. You should check out a variation between the maximum and the minimum of all those cases and get the maximum loads on the walls and the hopper. All right, so with that being said, these are my characteristics for the soil. And then we go to the pressure calculations on the walls and hopper. But before that, we need to get some values from our model itself. The first value is the top width, and I'm going to use the rectangular silo here in my calculations. There are slight differences between rectangular and circular. I will try to mention those, but however, for simplification purposes, I will calculate for the rectangle and basically use the same load for both rectangular and circular. This is an approximation and is some kind of an inaccuracy, but it's for basically time purposes that I will do that. Otherwise, I will just keep reiterating and rehearsing the same words over and over again with just telling you where the differences are. I will try just tell you where the differences are during this video. So we need the silo top width, and from the silo top width, we can calculate the perimeter. Notice that I'm using 4 multiplied by the width because I'm assuming a square silo. And the area. Those are calculations. I should basically format from that because I said that this is basically calculations. The Y start depth factor, this is taken from here from figure 6.3.2.1, which denotes or explains where the start of the load calculation should be, which is basically the centroid of gravity or center of gravity of the cone above the end of the silo. So it's 2 over 3 HS. In case it's a circular silo, well, I chose, of course, you can be on the safe side and assume a 0 here. I chose half S to be a little bit on the safe side. So the half you see here is basically an assumption I have assumed. I didn't assume 0.67, I assumed half. Which means, of course, the silo wall height is 9 meters, and this is something I've taken from Robot. The silo wall height is the height of the wall without the hopper, and I've taken this from Robot. And the hopper height is, well, also from hopper, from Robot. It's 2 meters. The angle of repose here, there is an approximation. Of course, the angle of repose, by definition, is the angle a pile of material will take if you just pile it up. Like if you take sand and pile up the sand, the angle of repose is the angle at which the sand is stable. My assumption here is that the angle of repose equals the friction angle. This is not accurate, so there are some references like Braja MDAS or something that might be giving you some guidance. I will assume angle of repose to be the same as the friction angle. HS is, as you can see here, the height of the cone under my assumptions of angle of repose, which you can calculate from basically delta x over delta y, because this is delta y, this is delta x, and you have the angle of repose. So HS equals half the width multiplied by tan theta. And this is what was done in here. You can see the calculations here. Of course, please notice one of the pitfalls in Excel is to forget to turn your angles into radians. For that, you need to multiply by pi and divide by 180 to get your angles into radians instead of degrees. So with that being said, well, you can see that there is a wall load start and a wall load end. The reason behind this is for me because I want to know when I apply my forces on Robot, I want to know from where to where I'm applying those forces, because you see, the start is not at zero. Like if you call this zero, you would think that the start should be at zero here and end at 9 meters here. Well, that's not the case because you have the cone here. So my start is actually at 2 over hs over 3, or in my case, half hs. And my start is here. So I'm using this here to say, like the wall load start is this, which is basically the hs multiplied by half. And my load end is basically the height of the wall. That's a no-brainer. RH is the ratio of the area to the perimeter, basically the ratio between what affects the gravitational loads versus what tries to help, which is the friction perimeter. And you can see that this is being used in this equation, 6.3.2.1, where you have RH. This is the RH we're talking about. So I calculated it on the side to kind of make sense of it. K is, well, the lateral earth pressure coefficient, which is 1 minus sine of theta. And G is a gravitational constant because you have here loads in density in kilograms per meter cube. So when you calculate anything without a gravitational constant, you will get kilograms per meter square. Of course, you need to multiply everything by the gravitational constant to get the newtons. So if you double click here, you can see that I'm multiplying it by G. This is a pitfall because it's not mentioned here. Here it's mentioned gamma, but of course we know that the gammas given in the table are in kilograms per meter cube. So you need to multiply by G. This is different a little bit. This is a little pitfall that you might fall in. Okay, so our calculations basically start. And I'm using a height factor because I'm discretizing my calculations because I want to get an idea of how the pressure distribution looks like. So I'm starting with a height factor of 0 to 1, meaning that I'm starting with y, and those height factors are relative to the height, and the height is between wall end and wall start. So my 0 here is actually at the wall start, and my 1 here is actually at wall height. But of course, I need to use this because the y in the definition here is measured from the centroid of the pile of soil or sand or cement that you have stored in the silo. So you need to be really careful about this. It's really a mind twister when you think about it. But well, I'm here, so I had to go through this twisting myself. This is a gruesome equation where you have to do everything. It's a long equation. What you see here basically is this equation used. So this equation 6.3.2.1a in full use. So you see all kinds of stuff, multiplications, divisions, exponentials, negatives. This is all included here. And this is the vertical pressure. So the pressure in the soil in the vertical direction. Even this shows you this. It shows you that Q is actually the vertical pressure at Y. What about the horizontal pressure? Well, that's an easy task because horizontal pressure equals K multiplied by vertical pressure. This is also further elaborated in equation 6.3.2.1b, as you can see here, which is basically also used here because I multiply this by the K factor. There is another load on the wall, which is the vertical loads on walls, and it's very important to include if you have really, really slender walls. I'll ignore it. I neglect it, and this is one of the simplifications I am using here because I want it to be a YouTube video. I'm not going to make it to be a lecture in a university. Although I teach at universities, in that case, of course, my university students will not see a neglected here, they will see values here. But well, YouTube videos are kind of different because I don't want the video to go on and on and on and on. My YouTube videos, at least the philosophy of CEE, is some kind of balanced. I want to include most of the information, but I will leave some things to intrigue you to think about them yourself. Tell me in the comments if you kind of agree with this or if you want me to go into painstaking detail about every single thing in calculations. So, okay, anyway, I'm neglecting the vertical load, although it's actually not that hard. I mean, the calculation is not mind-breaking, it's just this one. But I just keep it for you. I leave it for you to do it yourself. Okay. All right. So going on with the hopper pressure from initial filling, this is, and you can notice that in the Excel sheet, I try to keep calling out the sections which I'm using to, I'm referencing the sections I'm using in my calculations. Remember, I cannot show you the entire code, but for educational purposes, I can show you parts of the code. So this is what I'm using, 6.3.3.1. This is the initial pressure on the hopper from filling. And you can see this is basically Q0 plus gamma HY. Now, of course, what is HY? HY is the distance measured from the top of the hopper to the bottom of the hopper. So HI is between 0 and HH. Q0 is the pressure, the vertical pressure from 6.3.2.1. So the pressure of this equation at the level of the hopper, which means, in other words, that your Q0 is basically this one. Like the vertical pressure on the wall at the end is your Q0 at the hopper level. Now, there is some more information in the equation here. It says you have some thetas here. You can see it here. Now, of course, Qy is an easy task to calculate. It's basically the pressure plus gamma h. This is a linear model. So I have hi here. Notice that I discretized my hopper into less pieces because it's smaller. My wall was discretized at 0.1. I discretized my hopper at 0.25 because it's smaller. So this is the height factor, which will yield to you the height. Qy is basically the Q0 plus gamma multiplied by h. Notice that I'm also multiplying by the gravitational constant because kilograms and newtons. So I'm using that to find Qy. What about P? Well, P is not easy. Of course, I'm mentioning 6.3.3.1, B and C. So if you go to those equations, you see that you have two P's to calculate, and your P is the higher, the larger of those two things. So you need to calculate both, actually. So there is a theta and there is a theta prime. No, sorry, there is a theta and there is a phi prime. So what are those? Well, it turns out that theta is this angle, the vertical angle of the hopper. Now, noticing this, you can notice that the vertical angle of the hopper, the tan of this theta, is basically half the width divided by the hopper height. So you will see that theta is calculated by inversing arctan half width over hopper height. Remember, I'm using and assuming the rectangular silo here. It could be different. There is, of course, a simplification to notice that usually you have an opening here. So the true theta, they will notice that there is an opening here. So your phi should not be basically half width over h in tan inverse. No, it should be the width, half width, minus half opening divided by the height of the hopper. And that's correct. Truth to be said, you hit the nail on its top, so yeah, that should be done. However, I'm simplifying things, and I'm even writing here approximation to just like intrigue the viewers who want to have more. And this is once again what CEE does. It just intrigues you to think outside the box and outside of whatever you see in the code, because the code here is inaccurate. This is a surprise. It's not accurate because there is an opening here, but well, I'm here, so I have to tell you that. Of course, this is calculated by tan inverse half width over height. I'm multiplying by 180 over pi because it gives you radians, so I multiply to get the degrees out. Of course, I then regret that, LOL, or LOL, and multiply again to get it back to radians because it's used here, so I don't want to keep radianizing my degrees. The friction between the soil wall factor, this is important. Why? Because there is no mentioning, at least as far as I know, there is no mentioning of how phi prime is calculated in the equation for the hopper. This phi prime and here was never mentioned before how it was calculated, like in an equation. Turns out, if you check out the notation, and this is very important. Now, look, allow me to give you a small little piece of advice. The key of like being an all-rounder civil engineer is to be able to read codes. This is a no-brainer. This is a very important skill you have to master. Because trust me, nobody finishes his university knowing everything under the sun. You don't know that. The things you know when you finish university are basically the basics of design and calculation and analysis. You know how to design a building. You know how to design beams, walls, columns, maybe, steel structures in the simplest. But, well, you don't know how to design silos and don't expect to know to design bridges, depending, of course, on your university. So it's very important that when you want to try to design something new, it's very important you read the documentation, understand how to read the documentation. You see, those documentations are usually tricky because they keep throwing you back and forth. For example, here, look. It reads initial filling and it tells you, hey, Q0, go back to this equation. So it's kind of annoying, I know. It keeps throwing you back and forth in the code. So it's very important to be able to follow those code lines. And that's why it's also important to print out, if possible, at least the pieces of code that are relevant. The second thing I want to talk about how to read codes is this. For example, phi prime. You look up and down in the vicinity, you don't see anything about phi prime, you see it's used. So what do? Well, usually the ASI code has a notation chapter in the beginning of the ASI code. Like in the beginning of the ASI code, it starts talking about the notations used and the symbols used. You can see here, this is basically a list of symbols. And I want phi prime. So I go here, check out phi prime. And you see phi prime is the angle of friction between the material and wall of Hopper surface. So this is not the friction angle of soil. It's a friction angle between soil and your Hopper material, which is concrete or steel. And well, it's not mentioned in the code. So of course you can check out your internet and double check. But you saw this somewhere else. Now, I don't know, depending on university, but you studied in the book of Braja Mdas. This is a foundation book that I used personally when I studied, how to design retaining walls and how to check the retaining wall overturning and sliding and friction and so on. And phi prime was used in the sliding calculations where you assume that theta between soil and concrete is 2/3 multiplied by theta friction. So it's an approximation. So of course you can use this approximation to find the angle of friction between material and Hopper surface, and this is exactly what I've done here. See, I assumed this factor, and I think this is from Raja and Das. It's basically a factor that I use to multiply with the friction angle, which is 33 degrees, and multiply this factor to predict the friction between the soil and wall. This is what I'm trying to say. Don't just keep banging your head against the code. You will have to somehow try to find solutions to this, and that's what the channel is all about. Not only how to model in robot, at least this was the first part of it, but how to build on these modeling techniques into understanding the world and the structures around you and being able to design them. Okay, this was my little piece of advice. I just remembered that I think I messed up in my robot model. I'm just asking I think I did here concrete. Did I do concrete? Let me just check. I think I used concrete here. Let's take a look. Oh no, I did steel. Okay, I didn't mess up. I was like afraid that I remembered myself talking about steel and concrete friction angles, and I thought that I forgot to make this to become steel, but I did. So kudos to me, to my past me. Okay, so with that being said, well, now once again, I'm sorry. This is a highly theoretical video. You are used to me opening robot and starting doing stuff, but unfortunately, this time I cannot. This is a very long calculation, and trust me, the construction of this Excel file took around like more than I want to admit, even with my simplifications. Okay, so, and I will, of course, share it to you in the description. So if you check out the video description, you will see a link to the Excel file. So, well, with that being said, well, we need to calculate the pressures of the hopper. And how do I do that? Well, I need to find Pn, which is this long equation, which is done. So what you see here in Pn is basically from the equation of here. Now, that's not all, because, well, you see that you have two equations suddenly to calculate. You have equation here and equation here, and it wants you to select the maximum of those two guys. So, of course, I need to calculate them both, which I did. So you see here from this equation, and choosing the maximum between the two equations. The n is once again neglected. It's in the code. You can check it out. It's actually not really hard. It's basically the normal force multiplied by tan theta, which is the friction coefficient. That reminds me. I just got a little idea on camera. I want to try this. So, okay, wait. I'm just thinking loudly now. This is the friction angle coefficient, right? So basically, this should equal tan of theta prime, right? So if I tan inverse this, like if I tan inverse this, will it work? Of course, multiplied by pi, no, over multiplied on 80 over pi. I just got a little stroke of, so 30 degrees, right? 30 degrees. Huh. Well, that's a shame. It's a little bit different. Well, it was worth a try. I'm not really sure. Maybe, just this is an idea, and I wanted to think about it. Maybe, just maybe, I can calculate phi prime from the coefficient here of the friction against concrete, because you can clearly see that the longitudinal force is the pressure multiplied by the friction coefficient, which is basically from physics, like friction equals normal force multiplied by mu. So it seems that this mu is actually tan phi prime. So I think you can actually calculate tan phi prime from here, which is something, I guess. Not really sure. Wait, let me see something else. If I take this, the effective friction, and multiply by 2 over 3, do I get it? Oh, whoa, 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 look at this. Oh, this is nice. I think this is nice. So I'm using the friction angle between soil and wall. I'm using 2/3 multiplied by the internal friction, which is no way near tan inverse. So is it really that? Should I use this? Maybe. With that being said, well, we calculate Pn, and neglect Vn. So, all right. Of course, I'm plotting things because I want you to see. And finally, you have the wall pressure from flow. So now you finished our initial loading, and now we are in the flowing. Basically, when you open the silo for the first time. I'm saying for the first time because, well, the worst case scenario is the first opening of the silo, because in that case, your soil is at top maximum. Later, when your soil, I'm saying soil, but I mean your granular material, is at the top. Later, when you empty some of the granular materials, any later future opening will have less effect. So wall pressure under concentric flow, this is a very easy task. The 6.3.2.2 code paragraph tells you that you just multiply your static, I want to say static, pressure with a overpressure factor of 1.6. So basically, I took the data here and multiply this by 1.6, and end of the story. What about the hopper pressure? Now this is where things get spicy. You see, there is a chart that tells you what type of flow you have. If you have funnel flow or if you have mass flow. For me, before I do anything, because I don't want to mess up my entire assumption, I'll just say this. I will not change. It will equal this multiplied by this. When you go to hopper pressure, you need to know what kind of flow you have. You see the friction angle is 22 and the theta is 28. If you go to the shape 22, 22, something, you are here, you are in the mass flow, luckily for me. So I have a mass flow condition. Now, if I have a mass flow condition, this is the vertical pressure from the mass flow. And it's a somewhat strange equation. And it's a really not case to solve, because you think this is a cute equation, but it's far from cute. Because you have n that seems to be still cute, but it's not, because n needs b needs this, and this needs beta. So it's a long story, actually. I basically condensed into Excel sheet. Beta was calculated, and then, of course, in radians. Then B was calculated, and B chosen was calculated. Why B chosen? Because B cannot be less than 1. In my calculations, B was less than 1. Please notice that I'm assuming a plane flow hopper, so it was less than 1, which means, of course, plane flow hopper, because I am talking about rectangular silo. For the circular, I would have 2 multiplied by b. I will remind you that I will be using the rectangular loads on both circular and rectangular, which is an almost inaccurate move. But, well, you have the Excel sheet that I will upload to you, so you can use it to create your circular silo calculation sheet. Okay, so if you have b, you can calculate n, as you can see here, and from n, you can calculate this. That's not easy, so I made those little helper variables. Hi is the height, hh minus hi is just the helper factor because I have it here. Hh is the hopper height, and hy is the depth. So you can see that, well, you have those information. You get the qy, and notice something really strange. Notice something really, really strange I want to focus here and get to your attention. So allow me to put this in orange because I want you to focus on both those differences. The difference between this and this. You see, for all intents and purposes, with increasing depth, the pressure should increase because the depth of the soil increases, which means the load on the hopper or the gravitational pressure, the vertical pressure, should increase. But there is something really strange here. It seems that the vertical pressure decreases here. So what it is suggesting is that when your height or depth, basically when your HI is at HH, you will get zero vertical pressure, which seems to be strange in the beginning, but allow me to explain this in a moment. First of all, let me prove this to you. If your HY equals HH, then this becomes zero, this becomes zero, this becomes zero. You have all kinds of zeros here, which means that QY is zero. So as strange as it sounds, the pressure at the lowest point in the hopper is zero, although it should be totally different. And this is, of course, different from here. Like here, the pressure is increasing with more depth, so the lateral load increases with more depth. Here, the pressure is decreasing with more depth, so the lateral pressure decreases with more depth. But why is that? Turns out that there is a really good reason why this is the case. You see, you all know this problem in physics that you studied in the university. That is, if you are in an elevator, all of you have seen this problem in physics, that if the elevator is accelerating upwards, the registered weight on the spring is going to increase because it will not only register the weight of the mass, but it also will register the acceleration of the elevator. And if the elevator goes down, it's the exact opposite. It means that your spring will register less weight. And by the way, if your acceleration downwards is 9.81, you will experience weightlessness. So it means that the pressure that, or basically here the weight that you feel is dependent on the acceleration if it goes up or down. If your elevator goes down, your apparent weight is less. If the elevator goes up, your apparent weight is more. Now, how does this relate to the hopper? Well, you see, when you open the valve and material start pouring out, it means that your material is accelerating now. It's accelerating downwards. And of course, the material at the end of the hopper, when it's exiting, when the material exits your silo, it's under the gravitational acceleration, so it's weightless. Of course, the further you go inside, the less of effect you have for acceleration, because the material here is more than the material here. So you can calculate this from fluid dynamics, that V multiplied by A equals V multiplied by A, and you can derive an acceleration theory here, that acceleration multiplied by A for one side equals something acceleration A by the other side. What I'm trying to say is that, hey, this will accelerate at 9.81, but this will accelerate at less than 9.81. And the smaller the cross-section becomes, the higher the acceleration. The higher the acceleration, so the higher the weightlessness feeling. And this is why you see a very strange phenomenon, that in the beginning here you feel the full weight, and in the end here you feel weightlessness. So well, to finalize this video, I will basically do it in another video next time, because I think my recorder tells me I'm at the 40-minute mark. So of course I will video edit this and make it 25 or something. But to try finalize this, I finalize this by making simplification for YouTube video purposes. See, you have a case where you have initial loading conditions and a case where you have movement or emptying loading conditions. And for each one of those elements, wall and hopper, I'll be choosing the maximum load. So I put here from initial filling the pressure, the lateral pressure, and from flow the lateral pressure. Of course, the flow will win because you multiply by 1.6. So by default, this wins. And I put here the pressure from initial filling and the pressure from mass flow. And you see the strange thing. And in the beginning, you see that the flow pressure wins in the beginning, but then wins the initial filling pressure. Why? Now, first of all, what is this P? P is the lateral pressure measured from the mass flow. And the equation is found here, which is this equation, where we have this big thing here. So what ends up happening, and I have basically, to be honest, I have to revise my entire Excel sheet later, because I hadn't had time to check all the calculations in the Excel sheet. So maybe I messed up something. Of course, my dear viewer, if you find any error in the Excel sheet, please mention this in the comments so that I can basically fix that and upload an improved version in the next video. Anyway, you can notice that in the beginning here, you can notice that the first place, the flow wins, and the flow pressure is the pressure that's dominant. And in later stages, you see in the beginning here, the flow is dominant. In later stages, the initial filling is dominant, because in later stages, in lower depths, when you are near the exit, then your pressure here is almost zero because you're accelerating at the speed of gravity, at the acceleration of gravity. which means that, well, suddenly your mass flow pressure goes to zero, and what wins is basically the initial filling pressure. And you can see this by having this drawing. You see that this portion is controlled by the mass flow, and this portion is controlled by the weight, which is this one. So you have kind of a superposition or maximization between the two plots. Really interesting. So yeah, well, I have to apologize basically because I know you usually are interested in seeing robot in action, but this video is almost 40 or 45 minutes now, and I had to go into the details of calculating loads, and it was not fun. It was really long for me to produce this final product for you. Please notice that once again the disclaimer holds true that, hey, some loads are ignored and also it's for educational purposes, so please verify the Excel sheet before you use it. Anyway, I'm sorry to disappoint you, so I know you're all waiting for me to analyze and design this, but it took me far more time to prepare the Excel sheet than I want to admit. The final thing I want to talk about here, what I promise you next time, is basically the application of a bracketing. And this is where I want to tell you my plan. And a shout out to my dear subscribers, Nisapai and Donald Khanya. And what I will do next time, but I promise to give them an answer, is as follows. The question was of how to connect the leg of the supporting structure with the wall without having stress concentrations, because you see the connection here is a point connection, so you have stress concentrations. So how can you do that? You see, what I'm planning to do, and I will do this next time, what I'm planning to do is basically I want to use, there are multiple options by the way, I want to use a floor or basically shell element here to draw me a triangle, to draw me a little triangle like this, or like this basically. Yeah, like this, where the side of the triangle here is the hopper, and the column gets connected to this. Like I'm gonna do it like this. Like this is my plan. So I'm planning something like this. Like the column connects to the hopper. Sorry, the column connects. This is what I'm planning in the future. Like the column connects to a triangular shell element, and this shell element transfers the load of the column to the hopper. This is my plan. And this should mimic the little bracket you saw in the PDF file I have sent to you before, where you have seen some pictures of real-life silos. So that's the plan. And how do you do this? Of course. So one of the other questions my dear subscribers said is, when I did this numerical stiffening element here, I basically used or relied on what the mesh produced to me, the points that the mesh produced to me. Like if I just generate the mesh produced to me some points, and I used those arbitrary points to make my stiffening element. And even for my triangular bracket, I would need a point here. So am I going to use some arbitrary points here to do that? Well, the answer is no, and I will just show you what I will do, because, I mean, I know you want to see some robots, so well, at least let me try to give you some of the robot. What I'm gonna do is, you see in the edit, there's something called cut by plane. So you can cut the entire elements by a plane. It will generate for you points. For example, you can, of course, make a plane that is XY, and you can create nodes at intersections. And well, let's say that I want now, not a 3.5, let's say I want to cut with a plane that is at 10, 0, not 3.5, but 3.3, for example, so 20 centimeters. And I want to cut those things. I want to cut the funnel here. So I just go here and make sure I select only the funnel, which is going to be tricky. So let's select this, Control, and select this. I think I selected my funnel here. I think I did. And if I hit on apply, if you hit apply, you see that now it generated some nodes. I can actually do it right now by not only doing this, but also cutting the standing elements like this. So I want to cut this, for example, cut this, and cut this. So if you click on apply now, you see that those elements get nodes too. So now you have your triangle. You can actually do a triangle. Those bracings would have to be changed. Let me show you something. So if you click on the, so after you do this, you can see that, or maybe it's invisible, you can see that we generated a bracket here, which I can use. Now, of course, I need to shorten my column here and connect my bracings to the column here, or I might just leave it for the viewer to do it himself. But the point is that you asked how to make a bracket, and here is the technique I will be using in the next video. So I just wanted to tell you that, hey, I found a solution to this, and I will be implementing the solution next time. Anyway, this ends it for now, and as per usual, thank you very much for watching, and I hope that those videos are beneficial for you. Of course, if the videos are beneficial, then please like, share, subscribe, and comment. Also, try to recommend this channel to your colleagues if they're interested, if you think that the content is beneficial, because more subscribers helps increase the reach of this channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.